Okay, I want to start with this idea of what is a model or a theory, and I'm going to draw something here on the screen if I can get it right. Sort of goes like this. Not a very good drawer. And I think that the next line goes like this. And then there's another line that goes like this. And then there's something here like that. Does anybody know what this is? Hey, don't go ahead in the video. It helps if I say that we're here. Say I'm not very good at drawing. Maybe, if you've taken general psychology, there's something called the Rorschach test. And it kind of looks like a bunch of lines, and you're supposed to say what it makes you think of. Well, what this amounts to, and I'll show you this next. So what this amounts to really is the map of the Montreal Metro. At first, it just looks like a series of lines, and often that's what people think of a model or theory. It just seems very confusing. But when presented this way, people say, well, yeah, this is Montreal. But it's not Montreal. It's a representation of Montreal. So you could use this particular map, I would call it a graph, to be able to get around in Montreal, taking the metro. But you wouldn't be able to use it, for example, to drive in Montreal. It's not precise. But so we often say you should use the appropriate model or theory for the particular problem at hand. And one of the key ideas is something referred to as Occam's razor, is to eliminate the things that are unnecessary so that you can focus on only what you really want to examine or look at. But as I say, the relevant point here is that often people think of a model theory, well, it's not realistic. Well, this is not realistic as Montreal, but it's certainly useful to be able to understand how to get around in the city. They come in the form of a graph, like this here, for example, like a map. They can also come in the form of a series of mathematical equations, or they can finally just come in the form of words, a story of some sort. And in actual fact, these two are very similar because if you think about it, mathematics is just a language, a very precise one. I can show you something a little bit along the lines of what the scientific method is, which we're going to be discussing in a moment. I can use this graph to do that. If you think of for example, Berry-UQAM right here, which is the station in the center. If you know the station, it's rather complex. It's a complicated station. There's several lines that meet there. And this is particularly true if you've ever been to a big city like New York or Paris or Tokyo particularly, where there's many different subway stations or metros going in different directions. And think of a very busy station like that. Now imagine somebody coming to New York, Montreal for the first time. They happen to be at Berry-UQAM and they want to go to Montmorency. Well, what they would do is they would take, in effect, a map, or maybe look at the map, and then they would say, well, I think if we do this correctly, we should get on this particular line going in this particular direction, and that should get us to Montmorency. This is what we mean exactly by using a theory or a model to make some kind of a prediction. And then what the person will do, and if you've ever been in a large city with a complicated metro, you'll have done this. If you remember correctly, the station just above Berry-UQAM is, I think, is Sherbrooke. So what the person will do is, what I've done, and when I'm in a foreign city, is you look at the next station. You look out the window, you say, well, geez, is it Sherbrooke? What this amounts to is using a theory to create a hypothesis. You test the hypothesis by observation, and then you say, well, if it's Sherbrooke, then I think we're going in the right direction. We'll eventually get to Montmorency. If it's not Sherbrooke, then you reject the hypothesis, and you say, well, I'm doing something wrong. Now, in this case, it's unlikely to throw the map away and say the theory is wrong. You say, I'm just applying the theory incorrectly. But in a nutshell, in very simple terms, this is what we mean by the scientific method, which I want to look at next. Very a point I'll give you, the article you have to read is by Karl Popper about the definitions of science is whether you can make a specific prediction. Think of something like, for example, astronomy versus astrology. Astronomy makes a precise prediction about an eclipse, about the position of the star, particular planets or the moon or something, and it's testable. Something like astrology, on the other hand, the predictions are always vague. They always have a reason why they're not correct or they could be different. And so, according to Karl Popper, this is what defines science, is that the prediction is clear, definite, and can be rejected or accepted. As soon as you fall into things like, well, it could have been this, it could have been that, then it, according to Popper anyway, would not be defined as science. Very often in the scientific method, you're going to see the connection between two variables, the relationship between them. For example, we often think of somebody's income, their salary, and what their level of education is. Well, what is the connection between these two variables, and how are they related exactly? And often we'll be saying something like, well, if we change A, how does that affect B? Or if we change B, how does that affect A, and why? These are all things concerned with the development of a model and also the testing of that model or theory. I want to make this little point here too. What I've often found is that when we speak about an explanation, we're talking about a prediction. If you're capable of explaining a phenomenon, that's a bit like being able to develop a theory about it. It means you can lead to a prediction. Uh, if, on the other hand, all you can do is prediction and effects is before the fact. So we're now introducing the idea of time. Description, on the other hand, is often what I refer to as ad hoc. That means it's after the fact. Well, all kinds of descriptions after the fact can explain why such and such a thing occurred, but that's not really what I'd call a legitimate theory. It's simply ad hoc description after the fact. I want to make another point too. We'll be looking at this concept in the course. Is very often within a prediction there is random noise. That means to say the prediction is not perfectly accurate. There may be other events that are random that may distort or alter why the result is not exactly the way it was. And that's something that's very important we'll be looking at, as I say, because this is a quantitative course. I want to finish this section of the scientific method anyway, but just looking at some examples. I got these from textbooks, which means to say there is not one single scientific method. This one happens to say, notice the regularity. You'll notice certain constant concepts here. Notice the regularity of certain phenomena. That means to create some kind of theory, describe the theory, describe the phenomena, explain it. Notice the word explain here. This is a rather important one because we're saying, well, if you can explain it, that means you can develop a theory. You can lead to a prediction. Now, finally, they add the word control. Sometimes you want to control it, sometimes you don't. Here's another one, a little bit more complex. This is standard: review the literature, choose a method of investigation, collect data of some sort, organize, process the data. Here it says analyze and interpret the data. This is really the key part of saying, well, we're now going to test the hypothesis or test the theory, which is in essence developing the scientific method. I got this one out of Wikipedia. And I have to say very frequently this is what people do. Use your experience or knowledge, form some kind of a conjecture which amounts to a hypothesis of some sort. Use that hypothesis to make a prediction which amounts to being able to explain the phenomenon, and then test it. Another point here that I have to say, publish the results is a very important aspect, is that whatever you've tested, whatever results you've got, or whatever data you've accumulated, it should be possible for somebody to duplicate them. So you can't have some kind of hidden data and then you say, well, I did it, but nobody else can. I want to now look at the question of quantification. Notion of quantification is, consider the word blue or some kind of a number like this. Now, we've already seen this before. I saw it during the class, but this is actually, it looks like it's a series of numbers and letters, but it's actually a number in something called a hexadecimal system. Hexadecimal means there's 16 different numbers, not 10. So in fact, the hexadecimal system has the digits 0 to 9 and then A, B, C, D, E, F for a total of 16 in total. If you take these digits 0046B3 and type them into Google, you'll see something that looks similar to blue. What is the difference between these? Well, quantification is more precise. The word blue means blue, but is it dark blue? Is it light blue? Whereas we'll see with the hexadecimal, it's much more precise. In what way? Well, with hexadecimal system, there are 6 characters possible. Each character has 16 possibilities. Don't worry about how I've done the math here. It amounts to 16 million different numbers. That means to say there are 16 million different shades of color. This is how computers do coloring. By the way, they chose this specifically because the human eye is thought to be able to distinguish around 10 million different colors. By having 16 million, it means most humans looking at the screen would be able to detect wouldn't be able to really detect the tiny differences between different ones. As people get older, their eyes are not so good, so I probably can only distinguish between maybe 4 or 5 million. Obviously, different animals, it's a very different thing. So if birds were to be looking at a computer screen, they might see things very differently than a human would. Just for curiosity, if you want to, you just take this number here, 60DFE5, and type it into Google. By the way, Google search knows all about this, and so the guys that did the coding for it, they must have had a bit of fun because you can look at different colors according to these different schemes. Now, what are the advantages and disadvantages of quantification? Well, clearly one of the advantages is that it's more precise. Saying something is dark blue or light blue as opposed to saying it's the hexadecimal system, uh, objective. If we say, one person might say it's light blue, somebody else might say it's dark blue, but if we've got a quantification scheme, we can say it's objective. We can now compare very clearly between two different colors. For example, and it's not just colors, of course, it could be many other things. We're going to be doing something later, I'll talk about it in this lecture, the ability to generalize. That means to say, can we take a small sample or a small group and then generalize to a much larger group or the population? Also, we can verify or duplicate. And in fact, this is one of the big uses of quantification, is that if you think about it in terms of colors, is that if you want to have exactly the same color in a different place, well, it's easy to do if you have the specific number. Just consider this for an idea. Think of lipstick or paint. Uh, uh, I think lipstick, I didn't know this, but they go by names. So they have a whole series of names for different types of lipsticks, I guess colors. Paint is curious, it does both. If you've ever had to choose house paint, you'll notice that they often give a name and then they also give a specific number. So they're doing both. And I suspect it may have to do with the marketing. And some people prefer to have a name, some people prefer to have a specific number or code. They amount In this case, they amount to the same thing, but ultimately it amounts to quantification. It's a precision. Auto parts, for example, are typically parts for replacement parts for household items. Typically, you work by a quantification scheme. I've sort of found too that some people don't like quantification, and I think it's if you think of something like money or incomes or wealth, people are very sometimes uncomfortable with it, and I think part of the issue there is that it's just numbers are relatively new in human history. We've only had them for about, what, 30, 40,000 years, something like that. So I think it's not something that we're generally comfortable with. And one of the we don't take like is because of the precision of it. Um, I want to just give this quick idea of something. This is kind of an interesting concept. The first photographs date from about 1840 or so, mid 19th century. And I just found this example. This is, I think it's a photograph taken in the United States, but amongst the first photographs taken. People at that point began to realize that, think of it, prior to the 19th century, they had no photographs. They only had paintings. And they began to realize that really a photograph is just a series of dots. And in the case of photography, it's chemical. Now we understand that it's like what we call pixels. These are dots on the screen. And of course, the precision of the dots, each dot has a particular number indicating what the color is and then how bright or dark it is. And so it's just a series of numbers. Um, uh, Shortly after the invention of photography, well, it had an effect on painting. So here I've given an example, two examples of this. One is Monet and the other is Seurat. These are famous paintings, again, from the mid to late 19th century, where painting started, in effect, started to imitate photography. And actually, from that point on, paintings changed considerably because they no longer serve the role of being able to depict an accurate photograph, an accurate picture, because now we had photography doing the same thing. But if you look carefully at these photographs, you'll realize that it's a form of the beginning form of what's called pointillism, or just a series of pixels. I want to finish with this final idea of sampling. And what's called inferential statistics. It is one of the topics of the course. We'll get into it probably around halfway through the semester. Just imagine, for example, I've got a large population. For example, Dawson College. There's about 10,000 students at Dawson College. If you want, you can think of the population of Canada too, about 35 million Canadians. So imagine I take a sample of these 10,000 students at Dawson, for example, this class. Well, you'll notice I use a small n here to indicate the size of the sample. So I'm using n, that tells me there's 30 students. Sometimes they have a large n for the population, but in actual fact, as we'll begin to realize, population really means like the universe, which is big. If I use information from the sample, this class, for example, to generalize about the population. So I'm going to find out people's age or their height or what their R score is or some other feature about the person. It could be even their eye color. We call this inferential statistics. Perfect example of this, a political poll. They might sample, I don't know, 1,000, 2,000 people, ask them some kind of question, and then from those 2,000 people, try to generalize about how the election results when everybody votes in the population. Statistics Canada does something similar when they do a survey of the unemployment rate. They take a sample of people, ask them if they have a job or don't have a job, and then they generalize to the Canadian economy as a whole. We can go the other way, though, too. If I know everything about the population and I'm trying to predict something about a sample, this is quite different, and we refer to this as probability. For example, poker. Think of a poker game, there's 52 cards in the deck. We know everything about those cards. We know the hearts, how many spades and queens and so on. What we're trying to predict is what is the chance that I've got a particular set of cards in my hand of, in this case, n would equal 5. Now, the usual way of teaching statistics would be to start with probability and then later go to inferential statistics, but this is not a course in statistics. It's a course in quantitative methods. So generally, I will not be talking about probability, but I will be talking about inferential statistics, and I'll do it in such a way that avoids a lot of, I hope, with a lot of too many of the calculations and numbers involved. Although there's some basic, very basic calculations like what does it mean and so on we'll be doing later in the course. Final point I want to finish with is typically when we talk about something concerned with the sample, we'll be using Latin letters. For example, like X, which is the alphabet we use. But when we talk about the population, I'll be using Greek letters, like mu, for example. So, and this is a very nice thing about notation. In fact, I'll spend a bit of time on notation because it keeps things clear. So when I'm talking about the population, everybody together, I'll be using Greek letters. And when I'm talking about a sample or subsample or a smaller group of the population, I'll be using Latin letters.